correcting some mistakes at the end of my last talk. It's a bit embarrassing. So I want to go back to the polarizability of an ellipsoid, because this is an important thing. So the polarizability of a single ellipsoid. So suppose I have an ellipsoid and I put three axes on it, x, y, and z. Then the polarizability is going to be epsilon naught times the volume, and then it will be 1 over eta perpendicular times x hat plus 1 over eta perpendicular y hat plus 1 over eta, well, no, it's not eta, it's curly n parallel times z hat. Okay, so it's really simple. This is at the heart of the thing. Okay? Everyone is happy with this. So these are three principal directions, and these are the relevant, and so these are the values of the demagnetizing factor tensor. Okay, so now we can replace these guys by the identity, move things around, and then we can write this in the more customary form of 1/3 2 over n perp plus 1 over n parallel times the identity plus 2/3 times the anisotropy term times the usual 1/2 3 L hat minus the identity. So this is just rewriting this, and this direction is the same as the L hat direction. So this is no different from that. And now comes maybe the important point, is that if we now calculate the interaction energy of two particles, then, I mean, the procedure is really simple. We know that there's a spontaneous polarization. You calculate the field, that first term that Dick has just shown, the first term in the dipole the field of the dipole. Then multiply that by the polarizability of the second guy. That gives you the second dipole. Calculate its field. Calculate the energy of a dipole in a field. The energy of an induced dipole in a field is just minus 1/2 p dot E. And if this is alpha E, then you get the usual minus 1/2 alpha E squared. So one just calculates the interaction energy this way, and one gets this fairly simple result, minus 1/12 of H nu, and then we get the molecular volume squared over 4 pi squared times r to the 6th. So this is because of the r cubed dependence. And then the terms that I had by mistake last time, parallel plus 2 over this guy squared plus 1 over n parallel minus 1 over n perpendicular. So the anisotropy term squared again times P2 of the cosine of the angle between the two long axes. So this all pretty much follows along. And the point is simply that we can actually calculate pretty well the interaction potential of two dipoles. Okay, and now comes the question what to do next. So now we want to ask the question, suppose I have one molecule in a sea of other molecules, what is its energy? So we then have to consider its interaction with all the other molecules. So we have to multiply this term by the number density of molecules and integrate over volume. And then we get the energy, and I won't write out the the individual components because it's a bit long, but the energy of one molecule in the sea of its neighbors just becomes, so we have to multiply through by the number density, so we got a row here, and then we have to integrate, and then we integrate, we end up with a 1 over r cubed here, and then that'll be the lower limit of the integral. Anyway, when everything is said and done, we have this minus rho, and I'll call this u naught. It's just a collection of whatever guys are in there. And then we have some constant a plus b. And here comes the interesting part. Now, I'm going to have to average over all the molecules in a system. And so this is just P2 of L1 dot L2. And so I can use the addition theorem of spherical harmonics, split this into a product. And so here we just get SP2 of L dot N inside. So this is the energy of a molecule, the attractive energy of a molecule with all the neighbors. Okay? And so you can see there's an orienting potential now, which wants to orient this guy, and now we can start to think about the statistical physics. Except there's an important point, depending on your perspective, which is that this is really the energy of a pair of molecules. That's what we said here. So that's fine. If I want to know the torques on my molecule, this guy, then I want to look at the pair energy, right? But if I want to count the energy, I'm overcounting by a factor of 2, because this is really the pair energy. So imagine you have sort of two masses with a spring in between. You know, if I stretch the spring, that'll be a force, which I derive from the gradient of the total energy of the pair, right? But if I want to, I can't assign all of that to one molecule. So the way to get around this is to subtract from this half of its average. Okay, and then we get the right forces and torques, and we also get the right average energy. Okay, and I can do the same thing now with the excluded volume. And you remember that was the expression we derived before. And so we said that this excluded volume looked like V naught. And that too was the excluded volume really by two molecules. So I'll do the same thing here. So there was C minus D SP2 of the same argument here. And then I subtract again half of the average, so I have plus 1/2 ds squared. Okay, so now we have somehow dealt, however crudely, with the interactions, both the short range and the long range, and now it's time to ask, what do we expect to see? So we start by writing down the free energy. So Helmholtz free energy minus kT ln of some really complicated thing, right? So here we have minus all the, if you assume we have pairwise interaction, we have to sum all the pair energies we can think of. So we have to sum all the uij's, which are repulsive, plus all the uij's which are attractive over kT. So that's a total configurational Hamiltonian, so momenta are gone. And then we have all these variables, so these dq's are generalized coordinates. If I have n particles, I have that, and they are indistinguishable, so we have this. So dq, depending on your system, can be different things, but here we have position and orientation, so this could be dq bar, so we're integrating over all volume of center of mass, and then we integrate over orientation, which I just denote with d omega. Okay, well, so you look at this and you think, okay, but this is impossibly difficult, and there's lots of things that one can do and people do. But the simplest thing that you can say is, well, this is sort of hopelessly complicated, but somehow all the molecules basically live in the same world, so they should see the same thing. And so maybe we could approximate this by just looking at one molecule in some effective environment. And so people do that, so we can use Stirling here, and we can write an expression which is 1 over n times e to the effective energy, so effective potential of the particles. Now the attractive part is easy enough, so I'll just write here minus E attractive. Okay, so that part is fine, but the other part is more difficult, so let me just leave it the way it is. So that's minus U repulsive over KT summed over all the neighbors, and now I have to integrate over just one molecule, assuming that somehow these effective potentials embody what the other molecules are contributing in some average sense. So, okay, so this part is okay. There's no problem here, but this is really a mess. So we have hardcore repulsion, which is usually described by saying that we have a potential. If particles interpenetrate, energy goes to infinity. If they don't touch, the energy is zero. So now if you imagine integrating over volume only and leaving the angular part alone for a moment, then what we are doing here is we are moving our particle around in our box of volume V, and every time I bump into a particle, I have to put a 0 down, right? So this integral here over the volume just gives me the free volume available to one particle. And essentially all the problem is just to how to estimate this free volume. And you may not think that this is really so tough, but it's really tough. So we don't even know what the free volume is for hard spheres as a function of density. So it's really a pretty challenging problem. But we can sort of estimate that this free volume, write it here, I can imagine that is the total volume minus the volume which is occupied by the particles that I have. So it's going to be the number of particles, okay, number minus 1, same as the number, times Vx. Right? So this is the crudest estimate I can have. And if I factor out the volume, then I get 1 minus number density times the excluded volume. But I know from even the simplest considerations that this isn't really good. There's probably other terms here, but those are hard to get at. And so if you like cluster expansions and things, then you can get some handle on what that is. But I just want to do the simplest thing possible because time is short. So let me then approximate this. Okay, if I just look at this, and I can see I have this, I can just write this as e to the minus rho Vx. And I know you're thinking that's really lousy. But it turns out that it's not so bad, and if you do fancier density functional theory, that's what you would come up with. So let's just go with that assumption for now, and then you'll see that we end up with a volume here, so we get an inverse number density, and this guy becomes I can pull out the two terms that don't depend on P2, so this guy becomes essentially e to the rho UA over KT, and then I get a similar term from rho V naught C, and then what remains is an integral of e to the whatever we have, rho U SP2, and the other term that I get is plus DSP2, and I have a KT here, but I don't have a KT here. And then I integrate this over angle. So this is to the power n, and then I have a 1 over rho here. And when you just push this little calculation through, you get a nice simple result for the free energy, which looks like, I need to get to the optics part, otherwise we'll be out of time. So this is a free energy density now over KT, and I will write it in terms of volume fraction phi, which is rho V naught, and we get phi log phi. This is the usual thing that we always see. And then we see a power series, 1/2 phi squared A, not too interesting. Then we have 1/2 phi squared B S squared, and then we have minus phi log of the integral of e to the phi b sp2 of x dx. So I'm just writing x for cosine of, for L dot n. And that's it. And so let me say what A and B are. So these are just the coefficients we get, the isotropic parts of the interactions from the steric and the attractive part, which again we know pretty much explicitly. Okay, so these are things that we know, and now we can minimize the free energy with respect to the order parameter and get a nice self-consistent equation that you've probably seen. Looks just like the usual Meyer-Saupe, if you're familiar with that. Divided by the usual normalization factor e to the phi ds d2 of x dx. So the point is that even with kind of the simplest attempt at estimating the repulsive and the attractive interactions, we get this really simple form. And what is kind of interesting is that it embodies both aspects, both the steric and the attractive aspects of the interaction. So, oh yeah, so this was calculating, yeah. So now, if you solve this self-consistent equation here, you can do two things. You can assume that you ignore the steric term, and then you just get the usual thermotropic response, where you have the order parameter as a function of temperature. So it goes to 1 at low temperature, then it decreases, then there's a first order transition to the isotropic state. And of course, because we have the expression for the energy, you can look at stability and so on. And then if you do the opposite, if you turn off the attractive interaction, then you have order parameter as a function of density, which is sort of the Onsager story, except our kernel is slightly different from Onsager. So here we have then the attractive part and the repulsive part, just plotted separately. But if you plot the whole thing, then you get this nice surface. So this is the order parameter, this is temperature, and this is density. And so you can see what the thing looks like as a function of either one. So this is the temperature-dependent curve, the white ones, if you can see them, and the black ones are the density-dependent curve. And here's the energy, so you can sort out what the stability is. Now one can do this in a much better way, of course, but this is just a kind of a crude first-order approximation. And what I think is important is to try to keep track of both contributions, because we know that both are there. And it'd be particularly interesting to determine experimentally the density-dependent story. So anyway, this first part, supposed to have been done in the first lecture, was just to look at the simple picture of interaction, soft and hard, and what they lead to. And so there's lots of interesting work to be done here, essentially dealing with this free volume question. You can push a lot of the StatMech questions into just this question: what is the free volume of a particle in a dense system? Good. So this completes the first lecture, nearly. Any questions or comments on that? Good. So we'll press on. Now, what we have then is we have a picture where at sufficiently low temperatures and sufficiently high pressures, we have this orientationally ordered system where we have assumed that the director was somehow fixed in space and didn't vary in space. But of course, really, it can vary in space. These systems are soft after all. And so the next question to ask, which I think is a level above this, is what is the energy cost now of deforming the director field, which we assume uniform up to now. And so this is the Ossin-Frank theory, and it says that the free energy density associated with director distortions alone looks like 1/2 K1. I'm sure you've seen this many times. And dot del cross n squared plus K3 n cross del cross n squared. And so now how to calculate the Ks? I mean, that's an interesting question, how to calculate Ks. Well, basically, one has to go back to the intermolecular interactions and see what happens when the director is varying in space. And people have done this, of course. Yeah, so Misha Osipov has done this a long time ago, and he's still working in this area because it's a pretty challenging topic, as you can see, given that both steric and attractive forces are involved. So these k's, of course, depend obviously on order parameter, right? Because we know that S is somehow pulled out here. In fact, one could write this in terms of the Q tensor. And if you want to estimate dimensional analysis, would tell you that all we have is pneumatic isotropic transition temperature. And so these things should be KT and I divided by some length for dimensional reasons, which is typically a molecular length. Okay. Now, in addition to this, there's a null Lagrangian, so that would be K2 plus K4 times two terms, which is the trace of grad n squared minus del dot n squared. Okay? But this, even though it looks like a bulk term, is really a surface term, so if surface boundary conditions are fixed, then this doesn't contribute. There's one other thing that I need to mention, is that if we put this thing into an electric field, then there will be an additional term representing coupling to the field, and that is just minus 1/2 epsilon naught times epsilon parallel minus epsilon perpendicular times E squared. So this just comes directly from the polarizability. Molecules like to line up with the field, as I said, and this is just the bulk contribution. I want to take 1 minute to comment on the sign, because there's been some discussion here. So we all know that the energy density of the electric field in free space or in a material is positive. So how does it make sense to have a minus sign here? And it makes sense because we're assuming that the field is a constant here, and we are really fooling around maybe with, I'm sorry. Haste makes waste, E dot n squared. We are fooling around with the director here, and we are keeping the electric field constant. So we have to worry about the source. And so it turns out that the source, if you include the contribution of the source, then you would have this as well. So it's a kind of an interesting story. If you think about a battery, you can imagine that it's a huge capacitor. And your system would be a small capacitor. And so this capacitor is charged to some voltage, and then you connect these guys. And what will happen is that some charge will eventually go from here to there. And when everything is said and done, you will have 1/2 CV squared here. But this guy will have sent charge Q over there. So this guy will have its energy depleted by little c v squared. So this system will lose this much energy, and this guy will gain that much energy. And if you include that, that's why you have a minus sign here. I mentioned this because this is ubiquitous, that if you connect two capacitors, you have to lose half the energy. And this happens in mechanical systems as well. If I have an object here, and I'm coming along, boom, and I start to push it with velocity v, I have to put in twice as much energy as the kinetic energy of the guy, because half of it gets dissipated automatically. And so this seems a kind of a ubiquitous thing. Of course, if you don't do things at constant voltage, then things are different. If you don't do things at constant speed, things are different. Anyway, so much for that. If you want to do this differently, you could do it with a plus sign here and use D instead of E. And then one would get the same result, but here we would have to have the reciprocal of epsilon. Okay, so now we know that in addition to having orientational order, which wants to be uniform, we can also distort the system, and we can account for the energy in this way. And now I would like to switch to optics, because that's really where a lot of the liquid crystal applications are, and that's really what I want to talk about when I get to the bandgap story. So, maybe if we have time, we can come back to this problem, boundary conditions. Okay, so we want to understand light propagation in liquid crystal. And the concern, of course, is that it's an anisotropic medium. So, well, what we have is Maxwell's equation, so let's write these down. Del cross C minus dB by dt, del cross H, d by dt, del dot, no free charges, del dot d is 0, del dot b is 0, and we are done, except we have to link d and b to e and h. So we have e, which is, sorry, we have d, which is epsilon e, but we know that we can write this as epsilon naught e plus p, where p is the polarization, and this then becomes the dipole moment per volume, which is rho times little p, and little p is just alpha e. And so we have our polarization tensor coming in here.
What is your second equation?
Sorry?
Second equation.
The second equation.
No, not here. On the left, 4 equations. What is the second one?
This one.
Yes. Okay.
Thank you so much. Del cross H, d by dt. So epsilon goes in here. So we have to say what the relative. So we can write this as epsilon naught times epsilon relative times e, and so we have this tensor, but from the definition we can build it right away. And then the other thing we have is that B is mu h, but our systems tend to be non-magnetic, so we can just use a scalar mu naught here and not worry about any magnetization. Okay, now a point I want to make is basically this, that we know that in real systems, if I apply an electric field, the charges will move, and that will take some time. And so the response is not instantaneous, and if I apply some arbitrary electric field, I have to worry about the time response. So it's not simply a product. So if I go and I try to look at the system carefully and realize that it's a linear system, then I can use Green's function to write d in terms of e and time and epsilon and time. And because it's Green's function, I can take the Fourier transform and end up with this form of the constitutive equation. So whenever you see this type of thing in a linear system, then this must be in Fourier space. Now, if the system response is completely local, so just a delta function, then this is a constant and it doesn't matter. But normally this is something that one needs to worry about. Okay. Now to solve for epsilon r. And again, I won't go through all the algebra, but simply by noting that that epsilon is equal to epsilon naught times the identity, so that's the vacuum solution, plus rho times alpha average. We had the expression on the board a minute ago, so I can just write epsilon as epsilon perp times the identity plus epsilon parallel minus epsilon perp times n hat n hat. Okay, and I can write out these terms, but they're not really interesting. They depend on the order parameter s and the depolarizing factor tensor. So basically we have this, and we need to, I'm sorry, so this is epsilon r, which is epsilon divided by epsilon naught. And we need the inverse of this, and that interestingly turns out to be just 1 over epsilon perp times the identity plus 1 over epsilon parallel minus epsilon perp times n hat n hat. Little surprising, but that's what it is. Okay, so now let's see if we can get the wave equation and solve it. And that's kind of interesting because it's fairly effortless. So if we take the cross product here with del, then we get del cross E. We pull out mu naught, take the cross product again, then we get minus mu naught epsilon, which is now our tensor over there, and the second time derivative of E. And then if we assume that E is just a plane wave, some E naught e to the I k dot r minus omega t, this becomes just an eigenvalue equation. So here we have minus k cross E, and here we have omega squared mu naught epsilon E, and then rearranging things slightly, we have how do I want this? So this is the identity minus k hat. I'm going to divide through by the magnitude of k, look at k squared. And then on this side, I will end up with simply 1 over the refractive index squared times epsilon relative. Times E. So this is just the eigenvalue equation now. So we have this known tensor here, and then, but we don't know what n is. And so this is kind of the usual story. So n is really not a material property. It's an eigenvalue of some eigenvalue equation, and epsilon r is the material property. So we could look for solutions And one solution is kind of obvious. If the electric field is along K, then this side will go to 0. And so that means that this side must be 0 and must be infinity. N is the velocity of light, which is, sorry, v is the velocity of light, which is c over n. So if n is infinite, we basically have a standing wave. So this is a non-propagating solution and is not interesting. So E parallel to K is not interesting. And now we're interested in finding the propagating solution, which is a little more interesting. And it turns out that it's useful to switch to D at this point, because D is always perpendicular to K. So that's a useful thing. And we already have D here in essence. So to make a D here, I'll just insert epsilon inverse times D, and then we have right. Good. Okay, so now we just need to solve this eigenvalue equation. And so what do we have here? Well, first of all, how to think of this guy? Well, we know that it's real symmetric with positive eigenvalues. So if I think of d epsilon r inverse d being equal to, let's say, 1, then this is just the equation of an ellipsoid. Okay? Right? This is, if you think of r instead of d, right, then this is just the equation of ellipsoid, where the principal axes are the reciprocals of the eigenvalues here. So, okay, and so what we learn here then is that, well, so this is an ellipsoid, and then epsilon r inverse times d, which is really what I have here, what is that? If I have R matrix R equals something, take the gradient, I get the normal, right? So this is just the normal to the ellipsoid. And so here, I imagine this ellipsoid, let's imagine it. So this is not a molecule now, this is whatever ellipsoid is associated with this. It's called the index ellipsoid. And what I am saying is that let's imagine that I go to some point on this ellipsoid, and then I look at the normal here, whatever that is, that's this guy here, and then I have to project this on the plane, which is the normal to the propagation direction. So first of all, the axis of this ellipsoid is just the director. Right? That's the only anisotropy we have in the problem. And if I propagate in some direction different from that, k, so my wave is going this way, what I have to do is I imagine some d, any d times epsilon r inverse gives me the normal, and then I have to project that onto this plane here, right? This plane. Okay. Well, okay, I can do that. But that has to be in the same direction as this. Okay? So that means that this guy has to be a vector in this plane, normal to k. Right? Because I always end up with something in that plane. So then I say, okay, let's look at this from the side. So now I cut this ellipse with this plane, and then I will see some other ellipse in here, something like this maybe. And I'm asking the question, where shall I put my d so that what I have is going to be parallel to the normal? That's only two places, right? Either here, right, or here. And that's the whole story. So these are the two solutions, and we are basically done. So that's it. So you don't have to do anything other than that. You just imagine this ellipsoid defined by the inverse of the permittivity tensor, and immediately you can find the two values of d. Now, this is pretty simple, and this is called the ordinary mode. So this is always in the thin direction, so I get some elongated ellipsoid. So that's always in the thin direction of the ellipse. And the other one is more interesting. So this d is perpendicular to both the propagation direction. It's always perpendicular to that, and to the director. And E is also parallel to D. Everything is good. The extraordinary one is more interesting because here D is this way for sure. So the extraordinary one is we have D is in plane of N and K, but perpendicular to K. So that defines it completely. And so that's the other mode. And now, interestingly, if this is D, okay, then I have to multiply it with epsilon inverse to get E, and so I get exactly this. And we got that the electric field in this case is tilted back. It's not parallel to D. And so E is not parallel to D. And so this is really interesting because that means that now if you think about H, okay, del cross E, so it's going to be H is pointing out here, and the energy is going to be propagating not in this direction, but it will be propagating, if this angle is beta, is going to be propagating beta away from K. So this will be the energy, the pointing vector. And we have this, so if this is beta, we have this interesting story that energy is going at an angle. So the wave is going this way, but the energy is going this way. So the photons are going this way. And now photons, I have a picture of a photon somewhere. I have to skip stuff. Here's a picture of a photon. you don't see many of these. I just wanted to kind of summarize what all one has to think about. So photons have no rest mass, but they certainly have a wavelength. They have a frequency. They carry energy. They carry energy. Then they have linear momentum, which is in the propagation direction, and they have angular momentum also, which is just spin. So now in a liquid crystal, this interesting thing happens, that suppose that my director is this way, and well, I just have to rotate everything, and the wave is propagating this way, then what I find is that the energy is propagating in maybe this direction, somewhere between the wave direction and the director direction. And the photons in here, so these are the photons in there carry linear momentum in this direction. And so, I'm sorry. They carry linear momentum in the k direction. So they're going one way, carrying momentum in a different direction. So they're continually exerting a torque on a liquid crystal while they are propagating. So that's a pretty unusual situation. We're used to, if light is reflected, it exerts momentum. If light is absorbed, it exerts momentum. But here we have a situation, let me try to draw a better picture, where light as it goes, so suppose that the director is this way, and the wave direction is this way, so that's k. And we can imagine that these are molecules. And what we see is that light, the energy, the photons, let me use this red thing, that the photons are actually going in some direction in between k and the nematic director direction. So, and the photons are carrying forward momentum. So you can imagine that photon sort of enters one end of a molecule, comes out here, and there's a change, right, in the angular momentum. Because if I measure angular momentum from, say, this point, it's 0 here. There's no lever arm, whereas here, it's non-zero. So as the wave is going this way, photons are going this way, they continually exert momentum on this guy, and so this molecule wants to rotate this way. And so this is something that is quite easy to see experimentally. Okay, so I thought that it would be good to do something a little different, and so I brought a bunch of polarizers, and I know that most of you are familiar with polarizers, but I thought I'd pass them out just the same, and maybe I could ask you to take 2 of them, because it's better to have 2 than 1, because you can cross them and see what happens. And really what I wanted to tell you about regarding polarizers is that many animals can see with the naked eye the polarization of light, and so can we. We just don't know it usually. So I don't know where this is going. Yeah, so there's a fairly recent article describing in some detail how Vikings used to navigate by looking at the polarization of light. So what happens is that if you look at polarized light and everything is working right, then you will see a pattern which is like a kind of a yellow figure 8 and a blue figure 8, like this. So this is yellow and this is blue, and the blue indicates the polarization direction of light. So the polarizers I handed out have plastic film on them. So the first thing is that you should scrape those off, take them off, and they'll work a whole lot better. They have that on both sides. And then if you have it off, then you can cross them and extinguish light beautifully, which is a good thing to do. And then you could ask, what is the direction of polarization of light that passes through the polarizer? And you can sort of figure that out by looking at some reflection from some shiny surface. So if you have a metal surface and you look at light reflected from it, it turns out that the electrons can move easier this way than up and down. And so reflected light is pretty much horizontal, is polarized parallel to the surface. So if you extinguish glare with the polarizer, then you know that what's coming through is vertically polarized light. And I wanted to bring a calcite crystal because it's birefringent and really shows these two solutions rather nicely, but I forgot them at home, and by a miracle I found a mineral shop in Cambridge, and I got two beautiful calcite samples, so please pass these around. And if you put this on a piece of paper with writing on it, then you should see everything doubled and displaced considerably. And the polarizer is just so you can demonstrate that these two eigenmodes are indeed orthogonally polarized. And you can also figure out right away which is the ordinary and the extraordinary ray, because when you move the calcite, one of the two images moves and the other doesn't. The ordinary one doesn't do anything, it's the other one that moves. So this is not very profound, but I thought it might be amusing. And so if you then look at some ideally matte illuminated surface which is kind of featureless, and you persevere, then you should see Heidinger's brushes. And it's something that you can sort of learn to see better and better. And people can look at the sky and they can tell you which way light is polarized. And of course, it's sort of a useful thing because so this is the Earth, and this is you standing here, and you're looking at the sky at some point, and the sun is somewhere. And when you see light from the sky, that light that came from the sun and is scattered probably by density fluctuation, and what you see is the scattered light. And what we know from Maxwell is that the electric field must be perpendicular to the propagation direction. So the incident light must be in this plane, the light coming to your eye must be in that plane. So the intersection of those two planes tells you what the polarization should be. Okay? So, right. Well, I think it's about the right time, so stop here for a break. Thank you.